Okay, hi folks, this is the second of our videos covering questions in past papers about interference, and this time it is interference by division of amplitude. That's the air wedge and thin film interference, and as usual we're going to Mr Davies' interactive PDF of past papers, and we're going to have a little look at the 2018 paper question 11 and 2020 question 10. And as usual, it's a good idea to have a go at the question yourself first and then come back when you're ready and we'll show you how we have gone through it. So, starting with 2018, this is question 11 and it's about an air wedge. So, a thin air wedge is formed between two glass plates of length 75mm, which are in contact at one end and separated by a thin metal wire at the other end. And figure 11a shows sodium light being reflected down onto the air wedge, and a travelling microscope is used to view the resulting interference pattern. Now, I've already done a video of this very experiment, or you may have done it yourself, but there's the setup there. Sodium light is shining in, and the student observes the image shown in figure 18b by looking through the travelling microscope. So the student aligns the crosshairs to a bright fringe, and then moves the travelling microscope until 20 further bright fringes have passed through the crosshairs, and notes that the travelling microscope has moved a distance of 9.8 times 10 to the minus 4 metres. And let's bear in mind that that's 20 fringe spacings. So for part A, we've to state whether the interference pattern is produced by division of amplitude or by division of wavefront. Now remember, division of wavefront's the double slit experiment, so this is division of amplitude. And part B, determine the diameter of the thin metal wire. Now this is worth 4 marks, so that usually means it's a calculate question with a little bit extra. So let's go back to the diagram. There's the thin metal wire there, and it's that thin metal wire that is producing the air wedge between the two glass plates. And when we view the sodium light reflected from the apparatus, we see that interference pattern there. Now 20 fringe spacings was 9.8 times 10 to the minus 4 metres. So one fringe spacing, delta x, will be 9.8 times 10 to the minus 4 divided by 20. And that's 4.9 times 10 to the minus 5 metres. And we need that, along with the wavelength of the light and the length of the glass slides, to determine the diameter of the thin metal wire. Now the wavelength of the light isn't given, but we are told on the diagram that it's a sodium light, and we can look that up on the data sheet. And the wavelength of sodium light is 589 nanometers. So let's put that in our little list as well. 589 times 10 to the minus 9. We want to calculate d, the diameter of the thin metal wire, and the only other thing we need is the length of the glass slides. And that is given to us right at the very start of the question. Sometimes you've got to scroll all the way back to the stem of the question, and there it's there in the first line. There's two glass plates of length 75mm. So let's put in L is 75 times 10 to the minus 3 metres. And the reason we need all these values is because the relationship we're interested in is this one. Delta x equals lambda L over 2d. This is a relationship you can use to find the fringe spacing in an interference pattern produced on an air wedge. Let's rearrange it first because it's d we're interested in. So d will be equal to lambda L over 2 delta x, and then we can substitute all the values in from the list on the left hand side there. And if you do that all correctly on your calculator, you'll get an answer for d. The diameter of the thin metal wire is 4.5 times 10 to the minus 4 metres. Let's have a wee look at the marking instructions. So 11 part A, it's division of amplitude, and for part B, it's a 4 marker, remember. First mark was for working out the fringe spacing, and then it's a standard 3 marker for the relationship, the substitution, and the final answer with the correct units. Okay, moving on, part C. By measuring multiple fringe separations rather than just one, the student states that they have more confidence in the value of diameter of the wire which was obtained. Suggest one reason why the student's statement is correct. Well, you're going to be measuring a larger distance, and therefore the scale reading uncertainty will have less of an impact on that measured distance, and so the percentage uncertainty in delta x, and also in our calculated value of d, will be reduced. That's pretty tricky. Part D, a current is now passed through the thin metal wire and its temperature increases, and the fringes are observed to get closer together. Suggest a possible explanation for this observation, and this is worth 2 marks. And in these explain questions, it's always a good idea to refer back to the relationship again. So let's write that down. Delta x equals lambda L over 2d, and we're told that the fringes get closer together. Now, when the wire is heated, the wire is going to expand, so its diameter is going to increase, and the wavelength of the light and the length of the slide stay constant, so therefore the fringe spacing gets smaller. The fringes are observed to get closer together. There's the marking instructions for parts C and D. For part C, measuring multiple fringes will reduce the uncertainty in the value of delta x and d obtained, and in part D, 1 mark for saying the wire expands or the diameter of the wire increases, and the 2nd mark for justifying it in terms of all the other variables in the air wedge relationship. That's pretty tricky. The air wedge is always tricky. Anyway, let's have a look at another question, and this is from the 2021 assessment resource, which some people call the 2020 paper because it was written for the year 2020, but remember there was no exam that year. But schools were issued with it in 2021 to use it as part of the alternative certification model. And it is of course available on the SQA website and other good websites as well. And we're going to have a look at question 10 in this paper, and it's on thin film interference, which is another application of interference by division of amplitude. So zinc oxide is increasingly being used as an anti-reflection coating on optoelectronic devices, and this coating is shown in figure 10a, and the refractive index of zinc oxide, NZ, is greater than both the refractive index of the glass and the refractive index of air. Now there's a table of refractive indices on your data sheet, and air is there, it's 1.00, and glass is there, it's 1.51, so that might be useful to us. And we're also told that the refractive index of zinc oxide is greater than both the refractive index of the glass and the refractive index of air, so we could even put on there N for zinc oxide is greater than 1.51. Now this coating is non-reflecting for a specific wavelength of light to maximise the transmission of light into the optoelectronic device. And in part A, we have to explain briefly why a particular thickness of zinc oxide coating is non-reflecting for a specific wavelength of light. Well, for it to be non-reflecting, then light reflected from the top and the bottom surface of the zinc oxide will have to interfere destructively and cancel each other out. So in other words, a particular thickness of zinc oxide will produce destructive interference for reflected light. B part 1, state the phase change experienced by a light wave travelling in air when it's reflected from an interface with zinc oxide. Well, the zinc oxide's got a higher refractive index than the air, and you should know that when light goes from a lower to a higher refractive index, then it experiences a phase change of pi radians. And if you don't know what that means, then have a look at my video on thin film interference. Then B part 2, state the phase change experienced by a light wave travelling in zinc oxide when it's reflected from an interface with glass. Well, we were told in the question that the zinc oxide has got a higher refractive index than the glass, and when light is reflected from a material with a lower refractive index, then there is no phase change. Okay, moving on, 10 part C, the minimum film thickness D for maximum transmission of light into the optoelectronic device is given by the relationship D equals lambda over 2nz. And you might be saying to yourself, why is this relationship different from the one on the relationship sheet for the minimum thickness of an anti-reflection coating? Well, it's because of the single phase change at the top surface between the air and the zinc oxide. Anyway, we're told that lambda is the specific wavelength of the light for which the coating is non-reflecting. And in part 1, we've got a graph, and we're told the refractive index of zinc oxide is dependent upon the wavelength of the incident light, and the relationship between the wavelength of the light lambda in air and the refractive index NZ of the zinc oxide is shown in figure 10b. And we've to determine the minimum film thickness required to make the coating non-reflecting for light of wavelength 660.0 nanometers. That's to 4 significant figures. Now if we look at the graph then, quite a tricky scale here, because between 650 and 700 you've got 675.0. So 660 will be 2 boxes to the right of 650. There it's there, and that corresponds to a refractive index of 1.982. And that is what we're going to have to pop into that relationship at the top of the page. So let's write that again. D equals lambda over 2nz, and it's D we're looking for, and the lambda was 660 times 10 to the minus 9 divided by 2 times 1.982, and if you do that correctly on your calculator you'll get an answer to 4 significant figures of 1.665 times 10 to the minus 7. And I'm going to 4 significant figures because both the wavelength and the refractive index were to 4 significant figures. There's the marking instructions for part A and B and C, if you want to pause that and have a look at it. But notice C part 1 is given to 4 significant figures. Okay, C part 2. When viewed under white light, this zinc oxide coating appears blue-green in colour. We've to explain this observation. Well, remember it's anti-reflecting for 660 nanometers, and 660 nanometers is red light. So if it's not reflecting any red light, but it will reflect the rest of the visible spectrum, so blue and green is reflected. Now the rest of this question has got nothing to do with thin film interference. This is to do with the travelling wave equation. And we're given the equation for the light that has passed through the film into the glass. And there's the equation for that light wave there, where Y is the electric field strength of the light in volts per metre. That's the unit of electric field strength. And using data from this wave equation, we've to determine the speed of light in the glass. Well, it's back to your National 5 relationships now. We've got V equals F times lambda. And if you can recognise from this relationship where the frequency is, it's the 4.55 times 10 to the 14. And the wavelength, it's the 4.37 times 10 to the minus 7. Then it's just a case of popping both of them into V equals F times lambda, and that gives you an answer to 3 significant figures of 1.99 times 10 to the 8 metres per second. And that might ring a bell with you from National 5 when you were taught that the speed of light in glass is about a third slower than the speed of light in air. Anyway, part 2. The light wave loses energy as it travels through the glass. At one point in the glass, the energy of the light wave would reduce to 90% of its original value, and we've to determine the amplitude of the electric field strength of the light wave at this point. So this is energy and amplitude. And we can get the initial amplitude of the light wave from the travelling wave equation. There it's there, 1.6 times 10 to the 3. Sounds quite high, but remember that's the electric field strength in volts per metre. But let's jot that down just to remind ourselves, and then straight to your relationship sheet. And the relationship for energy and amplitude of a travelling wave is E equals Ka squared. And we can use that in its alternate form. E1 over A1 squared is equal to E2 over A2 squared. And then let's sub in everything we know. So the initial energy would be 100%. That's when the amplitude was 1.6 times 10 to the 3. Don't forget to square it. And that will be equal to 90% over A2 squared. If we rearrange it for A2 squared, then that will be equal to 90 times 1.6 times 10 to the 3 squared divided by 100. And then if you do that correctly on your calculator, then you'll get the new amplitude when the energy of the wave has reduced to 90% of its original value. And you get 1520, and what's your units here? A lot of people probably just put meters, but it's electric field strength, so it's volts per meter. There's the marking instructions for part D. It looks like 2 easy 3-mark calculations there, but pretty tricky in terms of figuring out what values to put into those relationships. And of course, what's your units? That's it for this video. Next time it's polarization. Might even get a wee tram question. And I've put a link in the description to my video of the air wedge experiment. That also includes all the theory about interference by division of amplitude and phase change. Anyway, see you in the next one.